Cosmic voids as curvature ridges. Cosmic voids are often described as regions where matter has been removed, pushed out, or evacuated by some active process. That framing quietly assumes that emptiness is the result of expulsion. This section inverts that assumption. Voids are not holes carved out of an otherwise uniform distribution. They are regions where accumulation never stabilizes in the first place. In a terrain-based view of spacetime, voids correspond to ridge-like or crest-like regions of curvature, where geodesic flow diverges rather than converges. Matter does not flee these regions, it simply fails to stay. The key distinction is between divergence and repulsion. Repulsion implies an active force pushing matter away. Divergence requires no such force. In curved spacetime, families of geodesics can spread apart naturally if the underlying geometry directs them to do so. In these regions, nearby trajectories separate over time. Matter entering such a region does not experience a kick outward. It experiences a lack of reinforcement. Small deviations grow rather than self-correct. Over long timescales, this prevents persistent accumulation. This makes voids the geometric complement of filaments and basins. Where basins funnel trajectories together and correct deviations, ridges do the opposite. They amplify deviations. Any slight imbalance in motion is not pulled back toward a central path, but allowed to drift further away. Matter passing through ridge-like regions continues onward into neighboring basins rather than settling locally. The result is not violent clearing, but quiet underpopulation. Because no active expulsion occurs, voids are dynamically calm. They do not host strong flows, shocks, or instabilities. Matter density remains low not because matter is being continuously removed, but because conditions for long-term residence are never met. This explains why voids are persistent. Once established, they tend to remain empty unless the surrounding geometry changes substantially. There is no mechanism within the ridge itself to reverse the divergence and create accumulation. Stability thresholds are central here. For matter to accumulate, trajectories must remain sufficiently coherent over time. In convergent regions, coherence increases. In ridge regions, coherence degrades. Even if matter briefly passes through, it does not linger. Over cosmic timescales, this produces large, stable voids without requiring any additional physics. Emptiness emerges as a passive outcome of geometry, not as a dynamic struggle. This also explains why voids appear smooth and featureless compared to dense regions. With little sustained accumulation, secondary structure has little opportunity to form. Interactions are rare. Motions are gentle. The geometry does not favor complexity there. Voids are therefore not unfinished regions waiting to be filled. They are complete outcomes of divergent constraint. Separating voids conceptually is important because they are often conflated with discussions of expansion, acceleration, or dark energy. None of that is required here. Voids do not need a driving force to exist. They arise naturally wherever spacetime curvature forms ridges rather than basins. Matter flows around them, not because it is pushed away, but because nothing holds it in place. Seen this way, voids are not anomalies in structure formation. They are an expected counterpart to filaments and clusters. Where geometry converges, matter gathers. Where geometry diverges, matter thins. The universe does not need to clear space to create emptiness. It only needs regions where stabilization never occurs. Established gravitational theory already provides the tools needed to understand voids as regions of divergent geometric flow rather than as areas actively emptied by forces. In general relativity, the behavior of nearby free-falling trajectories is governed by geodesic congruences, whose expansion or contraction depends on spacetime curvature. Where curvature induces divergence, neighboring paths separate over time. This is a purely geometric effect. No repulsive agent is required. Matter entering such regions simply fails to remain coherent long enough to accumulate. The formal description of this behavior appears in the Raychaudhuri equation, which tracks how bundles of geodesics evolve under curvature. When curvature terms favor positive expansion, congruences spread. This spreading suppresses the formation of long-lived overdensities without needing any mechanism to push matter outward. In other words, emptiness arises from failure of focusing, not from expulsion. This mathematical result is part of the standard relativistic toolkit developed following the work of Albert Einstein and does not depend on cosmological acceleration, dark energy, or additional fields. Numerical structure formation simulations within lambda CDM implicitly reflect this logic. Voids appear where the gravitational potential induces divergent flow, while matter streams along surrounding filaments into convergent basins. The simulations do not include a void force. They evolve matter under gravity alone, and voids persist because trajectories passing through those regions do not self-correct into stable orbits. Matter is neither pushed out nor heated away. It simply passes through and continues onward. This matches the ridge interpretation. Voids are dynamically quiet because nothing locally reinforces accumulation. Observationally, voids are characterized by low velocity dispersion, minimal internal structure, and long-term stability. These properties are difficult to reconcile with violent clearing mechanisms, but are exactly what one expects from regions of divergent geodesic flow. Surveys mapping galaxy motions around void boundaries show gentle outflow patterns toward neighboring filaments, rather than signatures of repulsion or evacuation. The absence of shocks or turbulence supports the idea that voids are passively underpopulated rather than actively emptied. Light propagation offers additional support. Gravitational lensing through void regions shows weaker focusing effects, consistent with reduced curvature convergence rather than any exotic dynamics. Photons traverse these regions along paths that subtly diverge compared to those near filaments and clusters. Again, the observation measures geometry. It does not indicate a force acting to remove matter. It indicates a lack of convergent constraint. Crucially, none of this requires introducing dark energy, accelerated expansion, or anthropic reasoning. The existence and persistence of voids follow directly from how curvature organizes motion. Where geometry forms basins, accumulation occurs. Where geometry forms ridges, stabilization thresholds are not met. Matter does not need to be expelled to leave emptiness behind. Emptiness is the natural outcome of divergent constraint. By grounding voids in divergent geodesic behavior, this interpretation remains fully compatible with standard observations and simulations, while clarifying the causal story. Voids are not scars left by removal. They are regions where geometry never favored residence. Their quietness, size, and persistence are exactly what established gravitational theory predicts when curvature selects against accumulation rather than enforcing it.